Drivers expect to speak to their cars the way they speak to another human, but traditional human-machine interfaces are rigid rule engines. Ask a legacy voice assistant a multi-turn contextual question, and the request often shatters against a wall of syntax errors. Automakers are now replacing those static command trees with agentic, generative AI copilots. These systems can process complex, multi-step inferences, resolving context across a continuous conversation without forcing the driver to repeat parameters. These models are becoming functional components within the car's active monitoring architecture. They act as a specialized interface for interpreting vehicle state, providing natural language explanations for internal diagnostic changes that were previously hidden behind dashboard icons. This requires a host architecture known as the software-defined vehicle, where the physical hardware operates within a continuous, real-time data flow network. However, inserting a billion-parameter foundation model into a kinetic, multi-ton machine introduces a severe engineering bottleneck. It creates a latency and safety paradox that automakers have to solve before these systems can operate safely on public roads. Looking at this simulation of cloud latency, we see the first failure state. If a vehicle relies entirely on remote cloud processing, performance fluctuates based on cellular connectivity. In dead zones, response times spike to over 2 full seconds, an unacceptable delay. Shifting entirely to local edge compute drops the response time to a lightning-fast 60 milliseconds, but the hardware triggers an immediate VRAM overflow error. The standard system-on-chips used for automotive infotainment lack the memory and thermal overhead required to run a GPT-scale model natively. They typically have only a few gigabytes of shared RAM to spare. To execute generative tasks safely, engineers deploy a hybrid edge cloud pipeline, backed by strict network isolation from the car's core kinetic systems. Figuring out where to process a driver's query, on the local chip or in the cloud, is the necessary first step for deploying an automotive AI. Volkswagen's implementation of the Cerence Chat Pro architecture provides a clear baseline for how modern software routing layers handle this compute trade-off. We see a voice command hit the vehicle's gateway, acting as a triage layer. Simple tasks, like climate control, flow to local databases for instant execution. For complex generative reasoning, the gateway routes the signal outward to the cloud. Before the data leaves the car, an anonymization protocol strips away the vehicle's identity markers and internal telematics. The stripped query is processed by high-compute enterprise partners, like Microsoft's Azure OpenAI services, which generate the response and send it back to the cabin. By splitting tasks at this gateway, automakers effectively isolate essential kinetic driving functions from external cloud dependencies. This separation becomes crucial when the system handles mechanical inquiries. Imagine a driver asking the AI why a red steering lock warning light has suddenly illuminated on the dashboard. An unconstrained language model risks hallucinating speculative repair steps. Advising a driver to perform incorrect mechanical actions is a severe safety hazard. To prevent this, the software relies on the traffic light safety interface, categorizing diagnostics into green, yellow, and red states. When a red critical state triggers, the system blocks the base LLM, routing the request through Retrieval-Augmented Generation. For a vehicle like a Mercedes-Benz C-Class, this RAG database is populated exclusively with the verified text from that specific model's official owner's manual. The generative AI is then restricted to summarizing the retrieved technical instructions into natural spoken language. It is mathematically prevented from inventing new troubleshooting steps. By anchoring the output to a closed knowledge base, RAG transforms the LLM from a free-form knowledge generator into a strictly constrained safety interface. Integrating these external cloud models into connected vehicles also opens up novel hardware threat vectors. In this vehicle schematic, core kinetic controls and diagnostics lie in the CAN bus and physical OBD2 port. Engineers must maintain a strict digital air gap, acting as a firewall that entirely separates the infotainment reasoning engine from these engine control modules. This physical separation is paired with a privacy protocol that deletes conversational history. When a mechanic accesses the vehicle for shop repairs, there is zero stored interaction data for third-party diagnostics tools to scrape. The conversational intelligence is physically and digitally barred from executing diagnostic commands or issuing kinetic overrides. While these guardrails are universal, The leading automakers balance latency, compute, and security constraints through distinctly different deployment paradigms. Honda utilizes a multi-partner strategy that leans heavily toward local edge processing. In this architectural matrix, Honda relies on partners like Sensory to run customized micro-language models directly on device, achieving sub-60 millisecond latency and bypassing cellular connectivity issues. Mercedes-Benz takes the opposite approach, prioritizing a high-performance enterprise cloud methodology. They utilize Microsoft Azure OpenAI and maintain a 1-hour dialogue history cache, enabling the system to resolve deep contextual queries over a long drive. To secure this constant cloud connection, Mercedes utilizes VIC-1 threat mapping, continuously monitoring the architecture against advanced driver assistance sensor spoofing and electronic control unit vulnerabilities. Returning to the matrix, Volkswagen represents a middle path, standardizing a strict hierarchical handoff protocol through Seren's Chat Pro. Their architecture prioritizes real-time query anonymization over long-term context retention, ensuring that voice interactions are deleted immediately after execution. Whether prioritizing edge processing speed or the analytical power of the cloud, each automaker constructs a bespoke gateway to manage the risks of foundation models. Before any of these software architectures reach a consumer via an over-the-air update, they pass through rigorous continuous integration testing pipelines. Engineers utilize the drive-safe risk taxonomy to establish a testing baseline, submitting thousands of adversarial or non-compliant driving requests to verify the model's refusal rates. Testing data packets move through automated scoring gates like BrainTrust, Luna 2, and Lynx, actively hunting for hallucinations. These inline detectors score responses in real time, instantly rejecting and rerouting non-compliant outputs before they reach the driver. This process of continuous, automated red teaming ensures that the traffic light safety interface remains intact under complex driving conditions. Ultimately, the industry's architectural trajectory is converging on hybrid, multi-agent systems that split tasks based on computational complexity. But the current compute balance is already shifting, as semiconductor companies like NVIDIA release new generations of embedded inference hardware. Open-source frameworks like TensorRT Edge LLM optimize local system-on-chips to run heavy vision language workloads without constantly pinging the cloud. Vehicles will run higher-parameter models directly on their own hardware, systematically reducing cloud dependency and latency. In the transition to software-defined vehicles, mastering this strict balance between edge speed and cloud processing will determine the safety, reliability, and ultimate success of these AI-integrated vehicle architectures.